Okay, it's 5:15, so let's rock and roll. It is my great pleasure to introduce DEVARSHI MUKHERJEE, who is currently at the University of Göttingen. Hopefully he will be at IMPAN sometime in March. And DEVARSHI, the floor is all yours. Analytic, cyclic, homology, and positive characteristics. Please go ahead.
Okay, thanks, Peter, for the introduction. Yeah, it's my great pleasure to talk here. It's slightly delayed. I was supposed to give this talk some months ago, but the upshot is that there are some more results I can talk about. So, okay, so let's get started. So let me start out by talking about the broad goals of the project. So the goal is to do non-commutative geometry of some kind in non-Archimedean situations. This typically means doing non-commutative geometry over, say, the p-adic integers or the finite field with p elements. And what we want to do is define a topological invariant for associative algebras over such rings. And of course, we also want to relate such invariants to other known invariants which are known from algebraic geometry or non-commutative geometry. A rather small list of known invariants is, let's say, homotopy K-theory, a topological K-theory, rigid cohomology, and Monsky-Waschmitzer cohomology. And it will become reasonably apparent in a bit why it is these theories that we want to talk about. Okay, so the first question is, why is this interesting to a non-commutative geometer? So one upshot of our approach is that we have an invariant for a widely studied class of algebras, at least at IMPAN, and this is the class of Levitt path algebras, which are a class of algebras which are obviously non-commutative, and these are naturally associated with graphs. And another geometric situation we want to talk about are group actions, say finite group actions on affine varieties over a finite field. And to such a group action, this can, well, there are two ways to study this. What we truly want to study is the orbit space of such a group action. And we can either talk about functions on this orbit space, which is commutative, but the issue is that such an orbit space is often poorly behaved as a topological space. So the other way to study such group actions is through cross-product algebras, which is also well studied by non-commutative geometries. And well, let's say a third interesting feature of this entire machinery, which we will develop, is that in order to do some kind of analysis which is inherent in non-commutative geometry or operator algebras, we need to have a set of analytical tools which really come from rigid geometry. So carrying over such tools from rigid geometry to non-commutative geometry is another interesting feature of this project. Okay, so let me start with a motivation which is actually not coming from non-commutative geometry, but from algebraic geometry and topology. So in algebraic topology or geometry, we want to study spaces or schemes. And to such geometric objects, there's often a lot that can be said by studying invariants on them. And the typical invariants which arise in this context are singular cohomology in the case of topology, or Betti cohomology in the case of schemes over complex numbers. Now, these are all, well, let's stick to Betti cohomology for a bit. This is a well-behaved cohomology theory which works over the complex numbers. And the idea is to find an analog which works in characteristic P. And well, this was a broad goal set out by Weil and Grothendieck sometime in the 50s and 60s. And it was postulated that the existence of such a theory, which is analogous to Betti cohomology and characteristic P, would have some deep implications in arithmetic geometry. And these were part of the famous Weil conjectures. So the idea was to study the Frobenius map, and more importantly, to study the number of points on a variety over the p-adics. And this was done through certain cohomology theories, which provided a number, and in some cases bounds, for the number of points in a variety, which are difficult to do by hand. And another point which I'd like to emphasize is that although these are commutative theories, any of these Bayes cohomology theories, often a lot can be said about the variety at hand if there is a non-commutative extension of such, if we broaden the domain to non-commutative algebras. And a particular thing that I have in mind here is the algebraic K-theory of a ring. And this is, as you probably know, a difficult object to compute. And it's in fact only computed by approximation to theories which are most naturally defined over all associative algebras and not just commutative algebras. And examples of these include the trace maps from algebraic K-theory to negative cyclic homology. So that's why a non-commutative geometer would be interested in such theories. So some examples of theories which were part of these Weyl conjectures and their non-commutative extensions are as follows. We have crystalline cohomology and characteristic P, which through recent work, which has kind of exploded, is topological periodic cyclic homology. And which is another thing which is used to compute algebraic K-theory in many cases. Another example is Analytic cohomology, whose non-commutative extension is a localized version of algebraic K-theory. Okay, so what goes wrong in characteristic P? Now, one can intuitively think that, let's say we talk about Rn or some other contractible space, these should not provide any cohomological obstruction precisely because they are contractible and are in some sense boring as topological spaces. And this is if we want a homotopy invariant theory. And if we want a homotopy invariant theory, it better provide zero or boring information for contractible spaces. And this is indeed the case with singular cohomology. So if you have a contractible space, then you get no cohomology information in degrees greater than 0. And the algebraic geometric situation is with algebraic de Rham cohomology over the complex numbers, which does precisely the same thing. Now, the reason why that is true is because of the Poincare lemma, which in characteristic 0 states that if you have a ring which contains the rationals, and if you have this polynomial algebra whose spectrum is precisely the affine n space, then this de Rham sequence is exact. And this is used to prove that the affine n space is contractible and therefore has 0 algebraic de Rham cohomology. And this is something which fails in characteristic P. And it fails because how you really prove this Poincare lemma is by taking differential forms and integrating them. And integration poses problems in characteristic P because you're dividing by numbers which could be divisible by a prime. So therefore, algebraic de Rham cohomology is undesirable in characteristic P, done in this very direct sense. So there are more indirect things one can do, which is lifting schemes over the finite field to something over, say, the p-adic integers. And this is the situation in crystalline cohomology. And these are, of course, very well-behaved theories for smooth and proper varieties. But again, you get these infinite dimensional cohomology groups in the case of non-smooth and non-proper varieties. Okay, so this is what is known up until this point on cohomology theories in characteristic P. Now, there's another. These are theories which don't really work in the case of non-smooth and non-proper varieties. Now, the theories that do work in some generality is rigid cohomology and its smooth approximation, smooth specialization rather, which is Monsky-Waschnitzer cohomology. And these are theories which are based on, whose definitions are based on the following approach, which we will use to define non-commutative extensions of these theories. So the idea is to take some scheme which is over FP, and the idea is to lift them to something which is better behaved. So if you just take the polynomial algebra FT, you want to lift this to ZPT, so the polynomial in one variable over ZP. This is torsion-free. And what the naive approach would be, of course, to define just the de Rham cohomology of this of polynomials in one variable over ZP. But this does not work either. And it actually also produces these infinite dimensional cohomology groups. So the idea then is to analytify these spaces in a suitable sense, which I'll talk about in a bit. And then we take the cohomology of this analytified object. Okay, so that was from the motivational perspective. Let me now talk about Monsky-Waschnitzer and rigid cohomology. I'll mainly be talking about Monsky-Waschnitzer cohomology because this is easier to define, and rigid cohomology is a generalization of this. So the setup is as follows. You have a complete discrete valuation ring, which for all I care is just the p-adic integers. You have it's a discrete valuation ring, so it has a unique maximal idea, which in my case is just P, a prime. The fraction field of ZP is the field of p-adic numbers, QP, and its residue field is the finite field with p elements FP. And what you want to study are varieties over FP, or its associated ring, which is its coordinate ring. So that if the variety is smooth, then this FP algebra is a smooth FP algebra. Okay, so this is the setup. And the idea is to lift such a smooth FP algebra to a smooth ZP algebra. And this can always be done in the manner that I've laid out. And what you want to do is you want to complete this in a certain sense, which is what I referred to when I spoke about analytification of these algebras. And this is really to ensure that your ultimate de Rham type cohomology theory that you define is well behaved. And this is something which reduces again mod P to the algebra you started with, so you're not adding any further information. And what this dagger completion is something I will refer to in a far more formal framework. But intuitively, what I need you to have in mind is as follows. Now, if you think of the, let's say, Tate algebras as analytic functions which are convergent on the unit disk, then these dagger completions are analytic functions which are convergent in a broader disk. So this is what I want you to have in mind. And these are also called overconvergent power series. And then the Monsky-Waschnitzer cohomology of this smooth variety is precisely the de Rham cohomology of the analytification and then localized at a prime. So you tensor with the fraction field. So you tensor with the fraction field in order to be able to divide by things, which is, as I mentioned in this Poincare lemma, you need to do in order to integrate differential forms. So that's the setup of Monsky-Waschnitzer cohomology. Now, I don't really want to define rigid cohomology, but it can be done in a similar manner. You start not with a smooth algebra in this case, you start with well, you start with a finite type algebra for sure. And what you do is you lift it to torsion-free algebra over ZP. And then you complete it with respect to its ideal, which gives you back the algebra you started with. And then you take this direct completion of this completed algebra, and then you again localize at a prime and then take its T-arm cohomology. So that's rigid cohomology. Okay, so let me point out some key features of this Monsky-Waschnitzer theory, which will be relevant to what we do as well. So Monsky-Waschnitzer cohomology is, of course, functorial for smooth varieties, and it's obviously homotopy invariant, which is the point of introducing this theory. And what you also know, and this is a very important result about Monsky-Waschnitzer cohomology, is that different choices of liftings all give you the same cohomology groups. And so rigid cohomology, as I mentioned, is a generalization to non-smooth schemes. And what's very important about rigid cohomology, which was not covered by Analytic or étale cohomology, is that it is also finite dimensional as a QP vector space. So in this sense, rigid cohomology is it gives you desirable results in all possible cases of interest. And it's also finite dimensional, unlike the bad behavior I pointed out of Analytic and crystalline cohomology for non-smooth and non-proper varieties. Okay, so this is the theory we want to generalize. And by generalize, I mean find its analog in the world of non-commutative algebras.
So just a silly question, if I may. What's the difference between smooth and very smooth? Because you said in your point two different choices of very smooth. Can you define it somehow or remind me how you do it?
I see. Okay.
What's the difference between smooth and very smooth lifting?
Yeah, I see. So for the time being, this is just so if you talk about smooth liftings, which are in some sense, it has some finiteness properties, then that's also very smooth. But for our purposes, you take any smooth lifting and you dagger complete it, it is very smooth. So that's what I have to say. I think this very was something I'd used in a previous slide, because these are the words by Monsky-Waschnitzer.
Okay.
And they did not ever use the word dagger completion. This was something that came up only later.
Okay, thanks.
Yeah. Okay. So the questions we address are as follows. Okay, so how do we define an invariant for non-commutative FP algebras using this machinery of lifting things, doing this very smooth or dagger completion, and then taking its T-arm cohomology or any kind of cohomology theory? And this is what I mean by this machinery. And let's say we define a theory, what are its expected properties? And such properties should, of course, model the properties that I mentioned in the Monsky-Waschnitzer theory, that different choices of liftings all give you the same answer. And as with the Monsky-Waschnitzer theory, it should be functorial for morphisms of algebras. And the third question is whether the theory we define actually specializes to Monsky-Waschnitzer or rigid cohomology, at least in some cases. And of course, finally, can we do anything interesting with this invariant that we define for at least the classes of algebras that I mentioned right at the start, say the Levitt path algebras or cross-product algebras? And in this talk, I will talk about a full computation of the theory we will define for Levitt path algebras. So let me point that out. Okay, so what is the perspective behind all this? So in characteristic 0, we know that periodic cyclic homology generalizes de Rham cohomology. And this is because of the Hochschild-Costan-Rosenberg theorem, which realizes Hochschild homology as a generalization of differential forms. And if you have a smooth algebra, then Hochschild homology gives you precisely differential forms. And then when you periodize it, you get periodic cyclic homology with the de Rham differential. And since rigid cohomology is essentially a de Rham type cohomology theory, one would expect that a similar approach should work with if we try to define a kind of a periodic cyclic theory. So just to make this point even clearer, the theories that I've spoken about so far, Monsky-Waschnitz and rigid cohomology, these are all homotopy invariant theories. And therefore, the non-commutative side of things should also reflect homotopy invariance of some kind. And the theory, therefore, to really look at has to be periodic cyclic homology.
Sorry, Devarshi, I have a request from the audience. I can hear you, but not very loudly. So there's a question, can you somehow be more loud?
Okay.
I don't know if by speaking up louder or doing something with your mic. Well, I can hear you, but it's really not so easy to follow you because it's coming from another room. And I just had a question from the audience, can you speak louder or by whatever arrangement with your microphone?
Yeah, okay. Let me just try out something. Maybe I'll switch to a different headset and check if that works. Is this better?
Ludwig, is it better?
I think it's about the same. Sorry for that.
Okay.
Also, Francesco was writing to me that there is kind of, I don't know, this dispersion of the voice. I don't know in your room.
This is a bit odd. I mean, I use the same setup for lectures. But... Okay, that's odd. But is it audible to some remote degree, or should I change the device altogether?
I think your microphone is not working, actually. It takes from the another one. So if you press the shield next to the recording and go to audio, there you can choose the other microphone.
Which shield and which audio? Sorry, really, okay, audio settings, you mean?
Yeah, if you go to audio settings.
Yeah.
And audio.
Yeah. Well, it's definitely selected, so my microphone is surely selected.
Oh, okay. So.
Yeah. Okay. Yeah.
Because it's not just loudness; it's just the quality. I mean, somehow your voice is like coming through a muffler. So.
Yeah. Okay. Yeah. I mean, if it gets really unmanageably worse, then I can just change to a different device, but that will be a bit disruptive.
Okay, I can understand you.
Okay. Yeah, I mean, I suppose the lecture is also getting recorded, so.
Yes, it's getting recorded, yes.
Okay. Yeah, okay, then I'll just have to apologize if you can't hear me completely, but I'll make sure that the slides from here on are more informative. Yeah. Sorry. Okay, so as I was saying, the natural candidate to look at to generalize rigid cohomology or any homotopy invariant theory should be periodic cyclic homology. This is probably the first thing we try out. And this is a paper by Cortinius, Joachim Kunz, Ralph, and Tamer. And this is the first approach they tried, which kind of started out this project. So here's the setup again. We start with a finite type algebra over a finite field. We take its free commutative extension, and we build what are called tube algebras, which are really, this is a construction coming from rigid cohomology and rigid geometry. And the idea is to take powers of this ideal and offset them by larger, offset them by negative powers of a prime. And this is a projective system of torsion-free algebras. And then the idea is to complete them in this dagger completion, which I talked about while motivating this. And again, I will make this precise when I start talking about the framework in which we do things. But just as another picture of what this truly means, we take infinite sums of this form, so pi to the j and s to the j plus 1. So we take larger and larger powers of some set or some module, and we offset them by higher powers of a prime. So the thing we get at the end is a bounded set. And this bounded set is in a very precise connotation, which I'll get to in a bit. And then we periodically complete these modules that we get at the end. Okay, and the result they have is that the periodic cyclic homology of this object that we built up is precisely rigid cohomology with coefficients in QP. And they also showed that different choices of free commutative algebra liftings yield isomorphic cohomology groups, and that's by homotopy invariance of periodic cyclic homology. But it's unclear how one can do this in if you take any lifting, and that's kind of the point of this Monsky-Waschnitz approach, that if you start with any algebra over a finite field with any suitably nice lifting, then the cohomology of that lifting should always be the same, no matter what lifting we choose. But this result is, as you can see, only for this specific kind of lifting. So therefore, we need a variant to make sense of periodic cyclic homology. And the variant is the title of this talk, that's Analytic Cyclic Homology. Okay, and broadly, this is the results that...
Sorry, could you explain what was this U?
Sorry?
Could you explain what is this U in the definition of this cohomology? Yes. HP lower star.
U
That's
is
the
this,
tube algebra.
U is this tube algebra.
Yes. Okay, I see.
Yeah.
Now I see. Okay. Mm-hmm.
Yeah. So, well, you can just for now think about it as tensor algebras, which go off through this Gunz-Quillen approach to periodic cyclic homology. So that's what U is.
Then you take the limit, right? Because you put infinity in your definition.
I see. Yeah, that's because we vary these ends. So this is a projective system of the algebras. So we vary these ends. Yeah. And that is then a projective limit, but in the projective category.
Yeah. Mm-hmm.
So that's this infinity.
Yeah.
Okay. So as I was saying, this is the main result that we probably have in this context. What we constructed is a functor from the category of torsion-free ZP algebras. And that's what so when I say pro-algebra, I'm really talking about projective systems of algebras. And these are complete in a suitable sense. And they're also torsion-free. So this is the category of algebras that we define a theory on. And this lands in QP vector spaces. And this theory we construct satisfies homotopy invariance, invariance under nilpotent extensions, excision, Morita invariance, and for smooth curves, or at least for smooth curves, this theory agrees with rigid cohomology. And for the remainder of this talk, I will talk about what these properties are all about. Okay, so like a necessary detour is to talk about this framework that we work in. And this is the framework of bonologies. Since I wasn't sure how many people have worked with this framework, I just thought it might be worthwhile talking a little bit about it. And this is really a framework to do analysis. That's what it is, and it's analogous to topology, where we formalize a notion of bounded subsets in the same sense that topology formalizes open sets in continuous maps. And this has been used now for several years by Ralph Meyer and Joachim Kunz and Vogt and so on for developing cyclic homology theories and representation theory. And most recently, they've also been used as a framework for derived analytic geometry. So if you don't know what this is and don't want to know what this is, then what we're really doing is working in the category of inductive systems of Banach spaces, where R is any suitably nice analytical ring. R can, for example, be the complex numbers, the real numbers, but more importantly, it can also be the p-adic integers or even the integers. And the definition, as I mentioned, is you start with a set, you give it a collection of subsets, just like in topology, and these need to satisfy some natural properties. I won't really get into what these natural properties are unless you ask me, but they really are natural. And the example that I need you to have in mind is the fine bonology, which is the smallest bonology one can talk about on a module. So any V module with finitely generated submodules, that's the fine bonology on a module. So that's one bonology I need you to keep at the back of your mind. And the other thing I need you to know is what completeness means in this context. And since we're talking about this p-adic context, let me just state that. So a module is complete if it can be written as an inductive system of p-adically complete modules. And another important thing to note is that completions always exist and can be explicitly built up in this manner. You write down a module that you start with, a bonological module. You write that as an inductive system of its bounded submodules. You p-adically complete these bounded submodules, and then you take its inductive limit, and then do some, well, let's say an analog of Hausdorffness, which is dividing out by the closure of 0. Okay, now a bonological module is torsion-free if multiplication by p is a bonological embedding. This is just the same as usual torsion-freeness. It's just that we're working in a bonological category, so we need our embeddings to also be bounded. And for all practical purposes, anything we start out with is already bonologically torsion-free. And the reason for that is that any torsion-free module with the fine bonology is already bonologically torsion-free. And as I mentioned, what we are doing is not really analysis, but finding an invariant for geometric-minded objects which don't carry a priori any kind of further analytical structure. So we just give them this fine bonology, which is a reasonable thing to have. Let's say you start out with a polynomial ring, then you just give it its filtration by polynomials of a certain degree. So, and this is always going to be bonologically torsion-free. And another, well, what I would say a highly non-trivial result is that completions inherit bonological torsion-freeness. And this is a subtle point because, as I mentioned, we start out with, let's say, ZP algebras and we analytify them. And the way of making that precise is through this kind of completion. And then we need to ensure that this completion does not destroy any of the nice torsion freeness properties, because that was the whole point of going from FP to ZP. And this is indeed the case, but it's a non-trivial result. Okay, so another definition I need you to know is that of semi-dagger algebras. This was what I was loose about previously when I was talking about these dagger completions and dagger algebras. So what you want again is, now that we have a framework to talk about boundedness, whatever the notion is, if you take powers of some bounded set, and if you can offset them by adding powers of p, then this is a way of enlarging your original bonology. And this is called the linear growth bonology. So what you do is you start out with a bonological algebra, you enlarge the bonology by adding these infinite sums, and then you complete them in the manner that I just mentioned previously, so in this sense. And this gives you the formal definition of a dagger completion of a bonological algebra. And this has its obvious universal properties, which is if you map into any such object, then the map from the original algebra to its dagger completion is the universal such map. And this is something which makes precise this Monsky-Waschnitzer completion to, in the sense that now we now have a universal property which describes it and a formal framework, which wasn't the case in this Monsky-Waschnitzer homology framework, where this completion that they defined was, in a sense, a bit ad hoc. So it was just defined so that the cohomology theory works. But in our case, this is through this formal bonological machinery. And of course, the important thing is that if we talk about, well, if A is the polynomial algebra and one indeterminate, then its dagger completion is precisely the Monsky-Waschnitzer completion. And as you can see, this now I can actually show you what this looks like. So this consists of power series whose p-adic valuation grows at least linearly. So this mu is this p-adic valuation. Okay, and another important thing to note is that this dagger completions of objects, this was defined also for non-commutative algebras. And this is another reason why we need this formal framework to talk about these completions. So you can't just talk about such power series as in the commutative case. Okay, so that's all I need you to know from bonology. So maybe this was a bit intensive in terms of notation. So just to repeat, you start with an algebra over, say, ZP. You do some machinery, you enlarge its bonology, and you complete them and get a nicely behaved object, which we call the dagger completion of the algebra. Okay, so how much time? Okay, so now is a second part of this talk, which is which may or may not be known again, depending on who you are. And this is this Kuntz-Quillen approach to cyclic homology. There are at least two ways of talking about periodic cyclic homology in the context of non-commutative geometry. One of them is through this BB bicomplex, which is defined canonically using the tensor product and the algebra. But there's another way of defining the periodic cyclic homology of a non-commutative algebra. And it is actually this perspective which explains the important properties of periodic cyclic homology. And this is due to Kuntz and Quillen. And this really goes by analogy with what goes on in algebraic geometry and Dian theory. So the objects you're interested in algebraic geometry are varieties, and analogously, the objects you're interested in non-commutative geometry are algebras. Smooth varieties, which are the desirable objects from the perspective of de Rham theory, are what are called quasi-free algebras in non-commutative geometry. And I'll define these in just a moment. And what often happens in defining, let's say, infinitesimal cohomology or de Rham cohomology of let's say a variety that's not smooth, is that you embed it into a smooth variety and then take the cohomology of that smooth object, defined in a precise sense. The analogous thing in non-commutative geometry is the resolution of an algebra by a quasi-free algebra. And this is a very important observation. And so in classical algebraic geometry, you then take the de Rham cohomology of some smooth algebra. And in non-commutative geometry, the analog of the de Rham complex is what is called the X complex of this quasi-free algebra. And the hope is, of course, that the X complex of this quasi-free resolution of an algebra actually coincides with the periodic cyclic homology of the algebra you started out with. And that is indeed the case, and quite remarkably so. Okay, so these are the analogies that I want you to have in mind. Now, what is the X complex? Here, R is any associative algebra. The X complex is defined as this very simple two-periodic chain complex, which is defined using non-commutative differential forms on one end and the algebra itself on the other. This B tilde is the map induced by the Hochschild boundary map, and this D is the universal derivation into an R bimodule. So this is a very explicit chain complex whose cohomology is supposed to give you periodic cyclic homology. And let me explain a bit more about that. Now, to really work with this Kunst-Quillen machinery, one actually has to work with projective systems of algebras and not just algebras. And the reason for that will become clear, but if you don't really want to get into the technicalities, you can just assume we're talking about an algebra. Okay, so what is quasi-freeness or non-commutative smoothness? This is defined by a similar extension property, which also is the way smooth algebras are defined. And this goes as follows. You consider extensions of this algebra where the kernel is nilpotent, and you want this to be linearly split. And when this linear splitting is actually an algebra homomorphism splitting, that's when you call the algebra quasi-free. Okay, so that's quasi-freeness. Well, analogously, smoothness in the classical algebraic geometric setting is defined in the same way. It is, if you take any nilpotent extension, then any morphism into such an extension extends into the thing in the middle. Okay, now what is periodic cyclic homology in this new setup? You start with an algebra A, you take its tensor algebra resolution, where the tensor algebra is a direct sum of these non-commutative differential forms. And then you take the completed tensor algebra, which is completion with respect to this ideal. And this resulting object is a projective system of algebras. And the important part is that the kernel of this completed tensor algebra into the algebra you start out with is nilpotent. And I put this in quotation because this is nilpotent precisely as a projective system of algebras and not as an algebra on its own. And of course, as I mentioned, whatever machinery you're doing should finally give you the periodic cyclic homology of an algebra that you started out with. And that is indeed the case. So this is, let's say, a new way of looking at periodic cyclic homology introduced by Kunz and Quillen. And moreover, if you take any nilpotent extension, then the periodic cyclic homology of the quotient is the periodic cyclic homology of the thing in the middle. So these are certain fundamental properties of periodic cyclic homology which are best explained in this Kunz-Quillen framework. Okay, so, and this is precisely the model we adopt to define periodic analytic cyclic homology. So we start with a complete torsion-free bond-logical algebra. As with the Kunz-Quillen framework, we build this tensor algebra extension. We take tube algebras. As I had defined previously, you take the powers of this ideal, you invert P, and take the sum of all of them, and then you vary the powers of the ideal. So that's the tube algebra. And that's precisely what is playing the role of this completed tensor algebra that I mentioned in the Kunz-Quillen framework. And of course, what you do is you complete this tube algebra in a precise sense. You have to take a relative dagger completion with respect to this ideal for technical reasons I don't want to get into. But for now, you can just assume that I'm doing the same dagger completion to this completed tensor algebra. And then you tensor this object with F. So now you really have a characteristic zero completed analytic tensor algebra object. And as in the Kunz-Quillen framework, you take the X complex of that, and that is the definition of our theory.
So what is an F? I understand it's some kind of a field, but is it completely arbitrary? What is F?
No, so F is the fraction field of this discrete valuation ring. So capital F is just QP.
Okay.
Yeah.
Okay.
Okay, so, and then, yeah, so this is, as I mentioned, this is a projective system object, and this is therefore a projective system of chain complexes. So you take its homotopy inverse limit, and then you take the homology of that. So that's just a small technical thing. And that's the definition of analytic cyclic homology. And what we finally have is an object in the world of QP vector spaces. Okay, so now the question is, so as I mentioned right at the start, we want this theory that I've now defined to have certain nice properties, which should be analogous to these Kunz-Quillen-like properties. And that's what I'm going to explain now. So first of all, it is homotopy invariant for a suitable notion called dagger homotopy. And the Kunz-Quillen framework, their homotopy invariance is for polynomial homotopies. Ralph, in his thesis, spoke about analytic cyclic homology in the Archimedean case. So over there, he referred to smooth homotopies. But the homotopy appropriate to this context is this dagger homotopy, where you use this Monsky-Waschnitz algebra instead of this polynomials. And yeah, so this gives you a notion of homotopy between morphisms, and it does what we expect it to do, which is if two algebras are dagger homotopy equivalent, then the analytic cyclic homologies are the same. Okay.
Sorry, can I ask a question?
Yeah.
Could you come back to the previous slide?
Yeah.
About this elementary dagger homotopy. Is the elementary dagger homotopy transitive, or you have to take?
Yeah, it's not. You have to take the equivalence relation, which is why I call these elementary dagger homotopies, and then you take the equivalence relation generated by them. And that's what is called an actual dagger homotopy.
So this dagger completion doesn't make this dagger homotopy, elementary dagger homotopy transitive?
No, no.
Relation. Okay, okay.
Right. So, okay, now I talk about the invariance properties of this theory. So an algebra is called analytically nilpotent if when we reduce it mod p, then it is nilpotent in the usual projective system sense. Another thing we need is a notion of quasi-freeness, analogous to this Gunz-Quillen notion. And here we just use extensions with analytically nilpotent kernels, and then we just ask the same conditions of it. That is, any linearly split extension with an analytically nilpotent kernel splits. Okay, and the result we have is what we would have hoped for in this Gunz-Quillen framework, which is if you have any analytically nilpotent extension with some bounded linear section, then the analytic cyclic homology of the thing in the middle is the analytic cyclic homology of this quotient. Maybe I did not mention this. Yeah, I did not mention this. So if you're wondering whether the set of all such extensions is empty or not, then there indeed exists an analytically nilpotent extension, and that's precisely this analytic tensor algebra. So this analytic tensor algebra, T of A, is analytically quasi-free, and its kernel is analytically nilpotent. And that also explains the reason why we defined our theory the way we did it. And an important corollary, which is used in most of our applications, is that if you start with an analytically quasi-free algebra, then its analytic cyclic homology is computed by the X complex of the algebra. And it turns out that if your algebra is commutative, then the X complex does the same thing as the de Rham complex. So your HA is really the same thing as de Rham cohomology if you start with an analytically quasi-free commutative algebra.
Sorry, but quasi-free and commutative means one-dimensional.
Yes.
One-dimensional smooth.
Yes.
Okay. Okay.
Smooth and one-dimensional is the same as quasi-free.
Yeah.
Okay. So now another property which we want our theory to have is excision. So if you start with an extension of some complete homological algebras with a bounded linear section, then there is a long exact sequence of QP vector spaces. So that's excision. Again, this is a highly non-trivial result, which is something we can obtain by adapting Ralph Meyer's proof of excision for periodic and analytic cyclic homology in the Archimedean case. Okay. So that's excision. And then there's stability in Morita invariance. So our theory also satisfies matricial stability and Morita invariance. What this means is that if you start with some complete homological algebra, and if you tensor such an algebra with some suitable matrix algebra, which I'll come to in a bit, then your analytic cyclic homology is the same, stays stable under tensoring with matrix algebras. Now, what do I mean by a matrix algebra? Includes the matrices, which are finitely supported functions on the set. It also includes the p-adic completion of this kind of a matrix algebra, and it also includes more general things such as matrix with entries which have certain growth properties. So these are the things we include in this class of matrix algebras. And of course, more generally, theory also satisfies Morita invariance for unit of algebras. Just a second. Okay. Now, an important class of examples, as I mentioned at the start, we now want to apply this machinery to a nice class of non-commutative rings. And these are given by Levitt path algebras. I'm pretty sure everybody at IMPA knows what these are, but I wasn't sure who else is going to be in this audience. So for their benefit, this is how they're defined. You start with a directed graph. and you define certain relations on such a graph. The first is this vertex relation. So you want these to be idempotent in this sense. And you have two edge relations. So the source of an edge times an edge should give you the edge itself, and so on. So you have these two edge relations. And you have two important relations, which are the Kunz-Krieger relations. And this is about isometries, and the second condition is the Kunz-Krieger relation, or Kunz. Well, I think they're both reasonably called Kunz-Krieger relations. But anyway, so these are some relations which you impose on your set of vertices, your edges, and edges with their paths reversed. And to this data, you can naturally associate two classes of algebras. The first is called the cone path algebra, which is through the first four relations. And the other is the Levitt path algebra, which is all the relations. There's another algebra which is called the path algebra, which is really the algebra generated by vertices and edges and concatenation of edges as multiplication. That's something I'll come to in a bit. Now, there's another thing you can define in this context. It's called the reduced incidence matrix. And this is really counting the number of edges between two vertices. Okay, so this is what we have in terms of notation about Levitt and cone path algebras. Now some examples for the graph with n loops. The Levitt path algebra of that is the Kunz algebra. Now, of course, the Kunz algebra in more C-star algebraic circles is really the C-star closure of this Levitt path algebra, but we don't really work with closures and completions of that kind. So I refer to the naked algebraic object as the Kunz algebra.
In general, graph C-star algebras are norm closures of Levitt path algebras.
Yeah. And for n equals 1, which is a rather important case, you get Laurent polynomials in one variable, and its cone path algebra is the triplets algebra. Another example, which is if you have this kind of line graph, then its Levitt path algebra is just matrices. Well, n is the number of vertices here. So these are some examples of Levitt path algebras. Okay, and we have a full computation for well, it's full if you have countably many vertices, but the computation goes as follows. If you, as I said, start with a complete Bond-logical algebra, then tensoring with a Levitt or a cone path algebra can also be computed. So in particular, if you take several copies of cone or Levitt path algebras, you can still compute them. And it gives you something in terms of this, of the co-kernel and the kernel of this incidence matrix. And of course, particular cases are the homologies of the cone and the Levitt path algebra. If you have a finite graph, then the analytic cyclic homology, we can say a bit more about the analytic cyclic homology because we can talk about tensoring it with this cone path and the Levitt path algebra. So if you have any information about the analytic cyclic homology of the algebra you started out with, this R, then you get additional information by tensoring it with Levitt path algebras.
Sorry, I have a silly question, if I may. I'm a bit confused by how do you get this R? Where does it come from? I mean,
R is
what if my arbitrary?
Yes, well, arbitrary in this category. So it's any complete Bond-logical algebra, which is why I said, so this, we can not only compute the analytic cyclic homology of this cone and this Levitt path algebra, we can also compute it for this cone or Levitt path algebra tensored with R, where R is arbitrary. And yeah,
Okay.
as I mentioned, the reason why I said that this n equals 1 case was important is because this specific Levitt path algebra, so Laurent polynomials in one variable, this is also a non-trivial smooth curve. And by basically taking this inductively, we can talk about higher dimensional varieties which arise this way. So, so therefore, in particular, we can put R as this Levitt path algebra itself and get some results in that direction.
So what are coefficients of this cone and Levitt algebras?
Sorry?
What are coefficients?
The coefficients, okay. So yeah, that I should have mentioned. So when you talk about this Levitt and cone path algebras, the generality in which you can define them any commutative ring. So which is why I thought it would be useful to mention this even in this audience, that you can really have any commutative ring and talk about its cone and Levitt path algebra.
So you can think about integers, for instance.
Sorry?
You can think about integers.
Yes.
Okay.
Definitely. You can think about integers, you can think about p-adic integers, you can think about complex numbers. Any commutative ring can be, you get the same results.
And this tensor product in this formula of in this theorem,
yes.
It is above what? Over what?
It's about ZP. So this
ZP. Okay. Okay.
Yeah. Okay. That's a brief idea of how this is proven, which might put things in perspective about why this R suddenly comes into the picture. So the way we prove this, and by the way, there are at least two different ways one can compute the periodic cyclic homology of Levitt path algebras. But, this one is one we found quite elegant, and it uses theorems by Cortenius in the classification of Levitt path algebras using bivariant algebraic K-theory. And this is how it goes. So you consider a functor from the category of V algebras to the category of chain complexes of V modules. And this takes any such V algebra to the analytic cyclic homology of R tensored with A, where R is arbitrary. And this functor is semi-split exact, polynomially homotopy invariant, and matricially stable. So this really uses the full force of the formal machinery we developed. And now, why I mentioned Cortenius's paper is because what algebraic bivariant K-theory is it's a universal functor from the category of algebras over some commutative ring to a triangulated category which satisfies these three properties. So semi-split exactness, homotopy invariance, and stability. So in particular, we have a natural map from the bivariant algebraic K-theory to this analytic cyclic homology of R tensor with A. So therefore, we can use computations of Cortenius to compute the analytic cyclic homology of Levitt path algebras. Of course, another thing we need is that this H is finitely additive and countably additive on V. And yeah, then by the universal property of KK, this map induces an isomorphism in analytic cyclic homology. So in particular, if you put R as V, then you can compute the analytic cyclic homology of the cone path algebra. Now to compute the Levitt path algebra, you need to make use of this extension. And since this functor H is semi-split exact, it maps such an extension to an exact triangle, and this is the exact triangle that is relevant. And then, of course, you can compute this. You can compute basically all the terms in this exact triangle. So you get now you use excision and get a 6-term exact sequence in homology. And this is how you compute the analytic cyclic homology of Leavitt path algebra and other algebras associated to it. And yeah, another thing which we just borrowed from this paper by Cortinius is a description of this induced map, which is really the incidence matrix, adjacency matrix. Yeah. Okay, so that's computing analytic cyclic homology for Leavitt path algebras using bivariant algebraic K-theory. I gather that it's also interesting to talk about another approach for computing things the way it's probably usually done. And that goes by a technique called cone localization. So here you start with a ring, say a commutative ring, and you talk about its category of finitely generated projective modules. And what you want to do is you want to invert a subset of morphisms in this category of finitely generated projective modules. Now, here's some definition. You call a ring homomorphism sigma inverting if this induced functor maps morphisms in this chosen subset of morphisms in here to isomorphisms. And
sorry, can I ask a question?
Yes.
So, like, do you have some reference for Leavitt path algebras have homological dimension 1? Like, in particular, also for the graph algebra counterpart and construction of this, like, you know, like projective resolution.
Yeah, well, I'm actually just going to talk about that. So,
okay, thanks.
I'll talk about it. This.
Okay, thanks.
Yeah. Okay, so yeah, that's why I was setting up this terminology. So what you want to talk about is a way of localizing things more generally. And the way of doing that is by considering this category of projective modules. And then you call a ring homomorphism sigma inverting if this induced map takes morphisms in sigma to isomorphisms. And localization in this sense is called cone localization. Now, unfortunately, this is not so easy to describe explicitly the way you would describe the localization of a ring usually by just inverting the elements that you want to invert. But it's a formal thing to keep in mind because the idea is that these Leavitt path algebras are actually cone localizations of path algebras. Okay, so the result is that if you have something which is analytically quasi-free to start with, and here you can also, since Alex asked the question, you can also assume it's quasi-free if you're talking about periodic cyclic homology over the complex numbers, then its cone localization inherits analytic quasi-freeness, whatever this cone localization is. I don't emphasize so much on what it precisely is because the way of proving this is just by abstract nonsense. So we don't really need to know what this ring looks like. But in our setting, we actually do, and there is some unpublished computation that we have, which gives this computation of the Leavitt path algebra as a cone localization. But this is how it goes. And for simplicity, let's assume the range of some edge is finite. Well, there are finitely many edges which point to a vertex. And let the graph be regular.
What do you mean by a graph being regular?
Well, vertices are regular. So the pre-image of the source at each vertex is both finite and non-zero, greater than zero.
So do you just mean that every vertex of your graph is a regular vertex?
Exactly. Yeah.
Okay.
Yeah. Okay, so then we talk about functions with finite support. Let S be the algebras of functions with finite support. And I define this NVW, which is the set of edges whose this alpha should be an E, sorry. So the source of E is W and the range of E is V, and you take the set of all such edges. And then you take the direct sum over such modules. And the tensor, this is a relative notion of tensor algebra, which I won't define at the moment, but this is just for the formal side of things, but it turns out that that is precisely the path algebra of this graph. And then if you take these functions which map, which are given really by row vectors of edges whose range is V. This is a bunch of row vectors, and this is where my simplicity assumptions come into the picture. This is really a finite row of vectors, of edges. And what we do is we localize at this set of morphisms between these modules over the Levitt path algebra. And it turns out that the Levitt path algebra is the cone localization of the path algebra at this set. So this was, as I said, just to set up some formal machinery to talk about the homological dimension of Levitt path algebras. And now we use the results of Kunz. This path algebra as a tensor algebra, I think, first appeared in Kunz's paper. This path algebra is analytically quasi-free. It's also quasi-free, and now I just use this theorem to deduce that the Levitt path algebra is also analytically quasi-free.
Sorry, but I'm a bit sorry if I might interrupt. Yeah. If I look at your second point, defining MVW.
Yeah.
So what you have alpha on the right, and you take the set over all E's. What's the connection between alpha and E?
As I mentioned, there was a typo. The alpha should be an E.
Okay. Okay. Good. Sorry, I overlooked it. And when you go below,
yeah.
What's the meaning? So alpha is just an edge which ends at vertex V, right?
Yes. Yes.
So what do you mean by such an E alpha? The partial isometry associated? What do you mean?
No, it just means alpha actually. Well, E alpha refers to an edge which maps to whose range is V.
So what's the difference between E alpha and alpha?
None actually. So I think I got a bit confused with the notations used.
That's very confusing.
Okay. That's to apologize again. So the usual C star algebra notation is S alpha, I think.
Exactly. Yes.
Exactly. So this is your S alpha. So
okay.
I think the C star algebra is good better with the notation. So S alpha really refers to the edge associated to alpha instead of alpha itself. But yeah, this is what I mean here. So this is just alpha. Yeah. Okay, so this is a proof that the Levitt path algebra of a graph has homological dimension 1. Okay, and then the main comparison result from the algebraic geometry perspective is with rigid cohomology. So here, if you have a smooth curve, as Tomak, I think, previously mentions, quasi-freeness in the smooth commutative case, well, these two notions agree. And these correspond to smooth curves in the geometric setting. So if you have a smooth affine variety of dimension 1 over a finite field FP, then the rigid cohomology of this curve agrees with the Monsky-Waschnitzer cohomology of this curve, and that agrees with the analytic cyclic homology of the dagger completion of the lift of this curve. Okay. So that ends this paper about analytic cyclic homology over ZP. Now let's talk about analytic cyclic homology, which is the stated goal at the start, which is defining a cohomology theory over a finite field. And here the perspective is that the ideas that were used in Monsky-Waschnitzer cohomology, for example, which is if you start with a smooth FP algebra, you can always lift it to something nice, which they call very smooth, which is just a smooth lifting, which is dagger completed. Now in the non-commutative world, this no longer needs to be true. So if you start with an FP algebra, this need not have a dagger algebra lifting, which reduces mod P to A. So the simple-minded possible definition, which is defining H A star of A as the analytic cyclic homology of this dagger algebra, this is not likely to work. So we need to define something more general. And in fact, we need to consider more general liftings even. So here we talk about liftings by complete torsion-free modules, which may or may not reduce mod P to A. The only thing we require is that these maps have finite rank on bounded submodules of W, and that these maps split by a bounded set theoretic section. So the main sort of meta statement is that to such a triple, we can functorially associate a Z2 graded QP vector space. And any two such liftings produce isomorphic QP vector spaces. And if we do have a nice lifting, then this theory that we define agrees with the theory that I've been talking about. And now, if you don't believe such liftings exist, then your W is just the free module over A. And that is complete torsion-free. And if the algebra you start out with has this fine bonology, which is the smallest bonology, then it also satisfies this finite rank condition. And yeah, so that becomes your triple in the most canonical sense, and that's called the analytic cyclic homology of A. Okay, but so far I haven't told you anything
May I ask
about
a question?
what...
Hello?
Yeah.
May I ask a question? If W is only a submodule, a module, okay?
Yes.
Do you generate from this W some replacement for this dagger algebra?
Yes.
Okay.
So, I mean, let me see if yeah, okay. There is a replacement. We basically do everything, because if you know the universal property of tensor algebras, these can be defined for modules as well. And it's actually the universal algebra which can be associated to a module. So if you start with this W, you take its tensor algebra, and then you have a map from the tensor algebra TW to A. Mm-hmm. And then that has a kernel. So then you talk about the tube algebra of the tensor algebra of W with respect to that kernel. And then you do the usual machinery. But again, over there are some technicalities. You don't complete it, you just enlarge its bonology, but you only complete it much later when you do the entire, when you take its complex. And that's getting into some technicalities which arise for some reasons I don't want to get into right now. But yes, to answer your question, that's exactly what is done. Okay, so what is the approach of proof? And as I mentioned, I haven't really even told you what this H A star of A W rho is. So let's keep that as a black box for now. So let me talk about what the approach is first. So if we start with any admissible lifting and talk about some if we start with some section for rho, then this canonically extends to a V algebra homomorphism by taking first the V module generated by A and then taking the tensor algebra on both sides. So on one side, you get the free non-commutative algebra. On the other side, you get the tensor algebra. And this, now by really putting a sequence of functoriality results, gives you a map from HA star to HA star A rho W. Now, the other direction is the more interesting and non-trivial direction. So, as I mentioned, I start with a complete V module. And this is where that very subtly plays a role. Now, it's taken to be complete because of some very nice classification theorems of what Banach spaces over the p-adic integers or QP looks like. And they actually all look like C0 functions on some set. So this is a very nice simplification in the world of Banach spaces and the non-Archimedean context. And I mean, as of now, nothing that I've spoken is stuff which could not have been conceived of in the Archimedean world. This is really one place where an actual honest difference comes in. So now that we know what any such module looks like, this C0 type of Banach spaces, it's, well, what we do is we explicitly build maps by taking a basis over here to this free module generated by A, and that's where the finite rank assumption comes in. And essentially any such morphism works. And then we apply the tensor algebra to both sides, and this gives us what is called a local algebra homomorphism. So this goes from the tensor algebra of, well, it actually goes from the tensor algebra of each C0 di, and that is actually an object sitting in the world of inductive systems. So you get a morphism which is locally defined, so on each bounded submodule, to this V of A, this free non-commutative algebra. And then again, you use this sequence of functoriality results to actually get a morphism in the other direction. And then comes a lot of homological algebra machinery in showing that this is indeed a quasi-isomorphism. And what one means by quasi-isomorphisms is this notion of local homotopy equivalences. So morally, it just suffices to look at bounded subsets of these chain complexes and build homotopy inverses on these bounded subsets. And if you change the category you work with to inductive systems of Banach spaces, then things just work out quite magically. And this was also how local cyclic homology is defined, just to give some perspective. And here, of course, some things still are a bit non-trivial and tricky. So when you talk about these local algebra homomorphisms, you can't dagger complete already at this stage. And that's because when you dagger complete, you no longer know what the bounded submodules look like so explicitly. So you just delay the completion to right at the end. And once you do that, well, the homological algebra is set up such that each of these constructions all give you or preserve quasi-isomorphisms. And what we finally get is a quasi-isomorphism. So the homology theories finally, as QP vector spaces, they're the same.
Sorry, is this quasi-isomorphism a homotopy inverse to this top one?
It is a
above other direction. You have a map in the opposite direction.
Yes.
Is these two maps mutual inverses up to homotopy?
Yeah, well, it depends on what one means by inverses. That's the thing. So, well, if you talk about the usual derived category, you localize at chain homotopy equivalences. But here we need to talk about more general equivalences. So the thing is that the map in the other direction is only defined on each bounded subset of this chain complex. So the homotopy equivalences are more general in that sense.
So you need derived categories, not only
Yes.
triangulated category of com of V.
Yes,
Okay, I
we
understand.
need a derived category. Yeah.
Okay.
Okay, and just to wrap up, the theory we define satisfies the following. It satisfies homotopy invariance for polynomial homotopies. It satisfies stability, and it satisfies excisions, at least for finitely generated algebras. That's still the point I've shown in my thesis. It's conceivable that it's also true for countably generated algebras, but that involves some more subtleties. I guess now that I'm basically out of time, I'll just mention a brief summary of these results. So what we wanted to do was define an invariant for non-commutative algebras in the non-Archimedean context. And this is what we have done so far. We've defined analytic cyclic homology for complete torsion-free algebras using the Kunz-Quillen approach to cyclic homology. And then we've also defined, we've used this theory to define a theory for FP algebras by lifting them to suitably define cube dagger algebras. And we've proven that these theories have nice properties such as independence of choices of liftings, homotopy invariance, stability, excision. And for smooth algebras of dimension 1, analytic cyclic homology agrees with Monsky-Waschnitz and rigid cohomology. Okay, I suppose I'll stop there.
Okay, thank you very much. Let's thank our speaker for his very nice talk. And we now open the session of questions.
Yes.
Please go ahead, unmute yourself and ask a question.
Can I?
Sure, go ahead, Tomer.
The first question, you started from Weil conjectures,
Yes.
which are related to Lefschetz numbers, the Frobenius, and,
Yes.
and so on. So assume that we have this our algebra A, which is the algebra of smooth functions on a fine one-dimensional curve, algebraic curve. And then we have the Frobenius.
Yes.
Can this Frobenius be lifted somehow to this analytic cohomology?
That's a good question. So the theory hasn't gone that far yet, but I think an important thing one would need to talk then about is whether the induced. So when you talk about this Frobenius map between algebras, you're talking about this induced map between cohomology groups. Now, what one needs to prove, and that has been proven in this rigid cohomology business, is that this is a map between finite dimensional vector spaces so that you can talk about traces. And that's what finally relates it to the number of points on the variety. So if you talk about smooth curves, then this is true precisely because our theory agrees with rigid cohomology. So it's true for smooth curves.
But my question is about this lifting. What is my problem? My problem is that if you have a non-commutative algebra over FP, then you cannot lift the Frobenius because the Frobenius makes no sense.
Yes.
And your resolution you are using goes even from, if you start from this commutative algebra, it becomes non-commutative, and then the problem of the lifting of the Frobenius is for me very mysterious.
Well, if you start with a commutative algebra, let's say it's from a curve, then you can also choose a commutative lifting. So this lifting, I mean, the point of this main result is that you can have any lifting which computes the theory.
Oh, so you mean that instead of quasi-free, you can take, first of all, instead of a tensor algebra, you can take a symmetric algebra? Or what do you mean?
Let me actually go back to the slides. Well, I mean, there is one thing which is used to define the theory, which is the tensor algebra. But the other thing is to use a lifting to actually compute the theory. So the tensor algebra is almost never compute the theory. So let's say you start with a nice affine variety over FP. You can always lift this to, I mean, in nice cases, there also exists nice dagger algebra liftings. And then you don't need to bring in the tensor algebra into the picture at all. That only comes in defining the theory.
Okay, so this Frobenius is only for these commutative liftings, these
Yes.
commutative resolutions in a sense.
Yes.
Okay, okay. And the next question is there a Chern character from K theory to algebraic K theory to this kind of homology?
Yes, so in dimension 1 again, you have a Chern character from homotopic K theory to rigid cohomology, even, because in dimension 1 they agree. But in general, you just for abstract nonsense, you always have a Chern character. This is something Richard and I are trying to work out now. So,
yes, but it would be a K theory of this resolution, in a sense.
Well, it will be K. So it depends now to a degree on what you mean by K theory. So as of now, there is no.
Oh, so you mean
K
about
theory
Kunz?
of a non-Archimedean ring, which is not algebraic K theory, let's say.
So do you mean that there is a Chern character for the Kunz K theory, the little k?
Well, a variant of the Kunz K theory. So let me state the honest result so far. So if your theory satisfies these nice formal properties, you always have a map from bivariant algebraic K theory, which is like the Kunz little kk. You have a map from that K theory to your homology theory. So it is like Kunz's kk, but again, the thing with Kunz's kk, so topological K theory, is that they're not in any obvious way defined in this non-Archimedean context.
Mm-hmm. Mm-hmm.
So you have a map from homotopic K theory to analytic cyclic homology.
So I'm asking this question because of the formal resemblance between the result of the structure of K theory of Leavitt algebras,
yeah,
and your computation of this cyclic periodic homology. So this incidence matrix and this kernel and co-kernel shifted by one. So so if there were such Chern character, so maybe with respect to this presentation, this Chern character would be identity in a sense.
Well, possibly.
Maybe tensored with something, tensor the coefficients, HA of these coefficients. Because the structure is the same. The structure is the same of K theory and periodic cyclic. Okay. Next question. You were talking about these elementary algebraic homotopies.
Yeah.
And also about the homotopy category of complexes.
Yes.
What is the device which can be used to prove that if you have this elementary algebraic homotopy, then this induces chain homotopy on the level of complexes. What was the idea of this computation? Because there are many ideas in homological algebra how to replace one kind of homotopies, how to move them, translate them from spaces or algebras to chain complexes. So what
is this a question about this stuff I mentioned right at the end about what I meant by quasi-isomorphisms?
No, because at some moment you were talking about the functors to the homotopy category of complexes. So com of V, I suppose,
Yes.
is a homotopy category of complexes.
Exactly. Yeah.
So it's a triangulated category, not the right category.
Yeah, that is a triangulated category. Yeah.
Yes. So if you have usually if you have these elementary homotopies, they induce chain homotopies on the level of complexes.
Exactly.
But in many places in homological algebra, different arguments are used for this translation. You can have arguments in simplicial sets. You can have argument in the RAM cohomology by this Poincare lemma or something like that for smooth homotopies and so on and so forth. So what device is used here?
Well, I think it's pretty straightforward. So if you have some dagger homotopy between two algebras, then the X complex is invariant under dagger homotopies. It's a computation.
So it simply works.
It simply works, yeah.
And there is no some idea behind this.
No, this was a fairly straightforward.
Straightforward. Okay.
Anybody else?
Thank you.
Any further questions?
Yeah.
Alex, go ahead.
So I'm not sure if I missed it. Maybe I hope not. Like this point, I'm like giving a canonical construction which would give rise to a projective resolution for Leavitt path algebras or its counterpart like graph algebras.
Are you still talking about the homological dimension being one?
Yes, exactly. So do you know some?
So yeah, I see. So there are some equivalent criteria for an algebra to have homological Hochschild cohomological dimension one. One of them is so you call such algebra as quasi-free, by the way, if you have homological dimension one. I think one of the ways of proving this, well, you either have a projective resolution of length one, or you equivalently show that any nilpotent extension of this algebra splits, and that's the same as quasi-freeness. So what I showed is that basically that this Leavitt path algebra is quasi-free. So I mean, I guess it's possible to come up with some length one resolution, but I haven't really thought about it. There are lots of equivalent criteria to show that things are homological dimension one.
So I'm just wondering because I mean, like, as far as I mean, like I read somewhere like that like there's like some canonical. So for example, in the world of C-star algebras, like there's this canonical Pimsner-Wolkolev triangle, Pimsner triangle, and that which then gives rise to like a projective resolution. So
well,
that's showing that every graph algebra has a length.
A few things change when you talk about the C-star algebra and not this Leavitt path algebra. I don't know if these very algebraic arguments even work in that context. But if you strictly talk about the Leavitt path algebra, then you don't need to come up with a particular projective resolution to talk about its homological dimension. It's what I can tell you now. I guess it's possible to come up with some projective resolution. I guess the bar resolution is always
But is there a concrete? Is there a concrete construction?
Construction of a resolution?
Yes.
Possibly. I don't know it right now, but it's quite possible.
I'm just wondering because I'm like, as far as if I'm not mistaken, this is like goes from this is from Raf's hands.
Yes.
Like, and
yeah, I mean, it's possible if you just take a look at the proof of this this result that I'm talking about, where length 1 projective resolutions are equivalent to some extension splitting. So if you show that your extension splits, then you can use this section and you can use this data somehow to come up with length 1 resolution. I'm pretty sure I can do this if you want to send it to you.
Yeah, so I mean, like, I don't want to hold you up for this. Like, I'm sure like you have other things. Like,
it's a good question to ask. I just don't know any applications of that. Do you know any specific place where you're applying this?
It would be good to know like a concrete like realization.
Okay. Okay. Yeah, we can talk about it.
But that's it. I mean, like, there's nothing more deep or so.
Maybe I can answer Alex. So there is nothing canonical about Pimsner-Vokulescu exact sequence. It's a spectral sequence. It happens to degenerate, but there's nothing canonical about it. So if you know that your algebra is projective dimension 1, then you can come up with a resolution of length 1.
But the Pimsner,
but it's not canonical.
But the Pimsner one is canonical, isn't it?
No. What's canonical about it?
I mean, like, at least
you have an algebra, right? You can represent it as a cross product, but you can represent it by a different cross product. And then it looks a bit differently.
Okay, yeah.
Okay.
Yeah.
So projective resolutions of length 1 are what? If they are of length 1, they are isomorphic in some sense, right? But they're not canonical.
So is that somewhat related like to like the non-canonical, so that like in triangulated categories that like you have like a non-canonical filling usually?
You have
non-canonical fillings in triangulated categories. Is it like somewhat related? Like
for example, yes.
I see. But do you have some reference for this anyway, even if it's not canonical?
I don't know. Boris, some reference to projective resolutions of length 1. Do you have one somewhere? Okay, he's not responding.
I know the general theory about
I am
projective resolution.
not sure of length 1 specifically.
Yeah,
not sure.
If you know that there is one that's a projected dimension 1, then can one just construct one using some procedure?
Yeah, I think this construction.
So also what we like DEVARSHI.
Yeah.
So also like on what you mentioned DEVARSHI, like related to this. I mean, like not just like general properties about projective resolutions of length 1, but I mean like what you mentioned, like DEVARSHI, if there's something.
If there's something as a reference or
something, yeah, some reference like.
Yeah, I mean you'll find most of this stuff in at least one of Ralph's books. So he's written up this homological algebra stuff pretty well, although not specific to any Levitt path algebra or graph algebra. But in general, if you know something is quasi-free, then you can find some projective resolution of length 1. It uses these non-commutative differential forms. I think that is a length 1 projective resolution. So this non-commutative differential forms is going to then be projective as a bimodule over this Levitt path algebra. And the projectiveness of that can be used somehow to come up with this length 1 resolution. I'm sure I can send it to you once I take a very brief look at his book. So.
Yes, I'm sure you know. Like, I mean, like I'm sure you've seen it like before. Like, so for you it will be easier. Yeah. Thanks.
Also, I missed it in the beginning. So when you mentioned crystalline cohomology and analytic cohomology for algebras over FP. Is there any comparison?
Well, from what I know, this crystalline cohomology is more closely related to topological periodic cyclic homology. I guess there is a comparison, but I'm not quite sure how to relate it to well, let's say this machinery we have for rigid cohomology. I think the analysis somehow doesn't interact so well with purely algebraic sheaf cohomological arguments. But I'd be very interested if there would be one.
I see. Okay. Yeah, thanks.
But I think TP recovers crystalline cohomology.
Yeah. Okay. Yeah.
All right. Anybody else? Richard, any questions?
No, it's okay.
You know it. Okay.
Yeah.
So
I'll have questions for him anyway. So, but
yes.
Not this kind of questions.
Not this kind of question. All right.
Richard has heard this talk multiple times. So.
Yes. DEVARSHI, so if you don't mind, I have some very non-deep, naive questions very quickly. So you are computing here some analytical cyclic homology of Levitt path algebras. How about just a regular old-fashioned cyclic homology of Levitt path algebras? Has it been computed? Can you, if I just give you, I don't know, the graph of a Teplitz algebra, and I think about just it as a Levitt path algebra, and I ask you, so what is its cyclic homology? Can you answer it?
I think I can, yeah.
Okay.
Well, so the computation, at least for periodic cyclic homology, it's just the same computation. That
it's just the same, okay.
Yeah.
Okay, okay. And another one is even more naive. You see, as you know very well, because you always have a gauge action on graph sister algebras, then you of course have a circle action, or if you're on Z grading on Levitt path algebras. But this means that every Levitt path algebra is naturally a comodular algebra of a Hopf algebra of a circle. So now every Levitt path algebra is naturally a comodular algebra. So is it interesting at all to consider some Hopf cyclic homologies that you might use once you have such kind of Hopf symmetry?
I'm not sure. It could be interesting in non-commutative geometry. So maybe you might tell me a bit more about that.
Okay.
But since we developed this from a slightly different motivation, which was related to rigid cohomology, we did not think so much in the direction of non-commutative geometry. But it sounds interesting.
Okay. Okay, I think so. It's already after 7 o'clock, so it's time to end. Thank you very much for your talk. Please send me your slides, okay? Please send me your slides.
Yeah.
And I stop recording now, and